Alright, let's take a look at example 2 here. Determining concavity. Determine the open intervals on which the graph of this function is concave up or concave down. Now, just like the last one, we want to take the second derivative and figure out where it is equal to 0 or where it is undefined. So here, we're going to have a quotient rule application. So we need the derivative of our upper function, and the derivative of this would be 2x. And we need the derivative of our lower function, and that's going to be also 2x. So let's see, the first derivative, f prime, is going to be low d high. So low d high, we're going to have 2x times our denominator function, x squared minus 4. Low d high minus high d low, 2x times the upper function, all over low low, x squared minus 4, that quantity squared. Now in the numerator we can distribute the two x's, combine our like terms, and when we get it cleaned up and looking pretty, our first derivative is negative 10x over x squared minus 4 quantity squared. So there's our first derivative. And now we want to take the second derivative. And it's another quotient. We are going to have to do the quotient rule again. So we'll move this up here. And, if we find the derivative of our upper function, d high, would be negative 10. And d low. To derive this, we're going to use the chain rule. Bring the 2 down front. And then we're going to have x squared minus 4 to the first power. And then our inner function's derivative would be 2x. And we apply all this into the quotient rule yet again, and we get our second derivative, f double prime of x. And once we get everything, all the common terms combined, it's going to look like 10 times the quantity, 3x squared plus 4. And our denominator is going to be x squared minus 4 to the third power. So we have our second derivative, and we have to ask ourselves, when would this equal 0, or when would it be undefined? Well, it's equal to 0 if our numerator equals 0. And here we have a 10. Inside the parentheses, we have a squared term, and we add something to it. So no matter what we plug in for x, squaring it will make it positive, times 3 is positive, adding 4 is positive, times the 10 is positive. So this numerator is never going to equal 0. But if we look to our denominator, there are going to be a couple numbers that would wipe out our denominator, turn it into a 0, and make the second derivative undefined. And if we just concentrate on inside the parentheses here, when does x squared minus 4 equal 0? Well, that would be when x is equal, or x squared equals 4, or at plus or minus 2. So we have plus or minus 2, our function is undefined, but it is never equal to 0. And just like we use the critical numbers and these numbers to chop up our interval. So we do have our intervals now. Again, the function does not give us left or right endpoints, so we're going to go all the way from negative infinity up to negative 2. And then we're going to go from endpoint negative 2 to positive 2. And then our last interval is going to be from 2 to infinity. And now again, we want to pick out some test values and put them into that second derivative. So here in our first interval, a good test value would be negative 3. If we plug that into the second derivative, we are going to have a positive output. A positive number comes out, and that tells us we're concave up. Our second interval, from negative 2 to 2, a good test value right in the middle at 0. If we plug that into the second derivative, we get a negative output. Negative output of the second derivative tells us we are concave down. And the last interval goes from 2 to infinity. Let's plug in a positive 3. In the second derivative, that's going to give us a positive output. And again, that tells us we are concave up. And here's our function again. Let's take a look at the graph of that. So here's our graph. Again, we are not defined at 2 and negative 2. So we took our second derivative, we chopped up our interval, and 2 and negative 2 are those numbers that chopped it up. We plugged in negative 3 for our test value. We got a positive output, so we knew that that part of the graph was concave up. From 2 to infinity, we plugged in positive 3. We had a positive second derivative, so that part was also concave up. When we plugged the test point of 0 in, we got a negative second derivative output, and that told us at that interval the graph was concave down. And now let's talk about points of inflection. It says the graph in figure 326, and I have that right here. This graph has 2 points at which the concavity changes. If the tangent line to the graph exists at such a point, then that point is a point of inflection. So here is our critical number, and we have a tangent line here, and we can sort of see it's kind of subtle in this graph. But if we look at this first stretch here, we can see that it's slightly concave upward, concave up on this interval. And then in the middle, this is a little more easy to see, we are concave down from negative 1 to 1. And then here where it changes again to concave upward, these are our points of inflection. It is where our concavity changes from up to down or down to up. So 3 types of points of inflections are shown in figure 328. So it says here, the concavity of function f changes at the point of inflection. Note that the graph crosses its tangent line at the point of inflection. So here we have our point of inflection. The tangent line's in blue. To the left of it, we're concave up. To the right of it, we're concave down. Here the graph has a horizontal tangent line at this point of inflection. And it's easy to see above the graph, here we are concave upward, and here we are concave down. And we could even have a vertical tangent line at our point of inflection, and we can see to the left here we are concave in the up direction, and above that point to the right of it we are concave down. So here's our official definition of a point of inflection. Let f be a function that is continuous on an open interval, and let c be a point somewhere in the interval. If the graph of f has a tangent line at this point, c comma f of c, then this is a point of inflection of the graph of function f if the concavity of f changes from upward to downward or downward to upward at this point. So to locate possible points of inflection, you can determine the values of x for which the second derivative, f double prime of x, is equal to 0, or for which those points do not exist. This is similar to the procedure for locating the relative extrema. So here is our theorem, theorem 3.8, points of inflection. If c comma f of c, that's just our x and y values, if this is a point of inflection of the graph of the function, then either the second derivative is equal to 0, or the second derivative does not exist at that given point. So here let's do an example to find some points of inflection. So here it says determine the points of inflection and discuss the concavity of the graph of this function, x to the 4th minus 4x to the 3rd. So when we were finding relative extrema, we set the first derivative equal to 0. Let's find the first derivative, 4x to the 3rd minus 12x squared. But we're not looking for the relative extrema. We want the points of inflection. And to find that, we're going to take the second derivative. So f double prime of x. And we'll just derive it again. 4 times 3 is 12. X to 1 power lower squared. Minus 2 times 12 is 24. X to the first power. Now we have our second derivative that we set equal to 0. And here on the left we can see in each term we have some common stuff. We can factor out a 12 and an x. So we factor a 12x out of the first term, we're left with an x minus 2, and that's equal to 0. And then, of course, we set each term equal to 0. When 12x equals 0, we know that x is 0. When x minus 2 equals 0, we know that x is 2. So this is going to chop up our intervals. So there's no specified left and right endpoint, so we are going to go from negative infinity to our first critical number 0, and then from 0 to 2, and finally from 2 to infinity. Now we're going to pick a test value out and plug it into our second derivative, a lot like the first derivative test. So here between 0 and negative infinity will be negative 1. And if I plug that into, I like to put it in here, because we have two terms that we're multiplying. If I plug negative 1 into the first term, I'm going to get 12 times a negative number, which is negative. And then here, in the parentheses, I'm going to have a negative 1 minus 2 is a negative 3. So I get negative times negative, which is positive. So the sign of our second derivative is positive, and that tells us we are concave upward. Okay, now I'm going to pick a number between 0 and 2. Right in the middle is 1. What happens when I plug a positive 1 in here? Well, 12 times positive 1 is positive. I plug a 1 in for this x. 1 minus 2 is negative, so I'm going to have a positive term times a negative term, which is negative. And that negative second derivative value tells us we are concave down. And our last interval, from 2 to infinity, let's plug in a 3. If I plug a positive 3 in here for x, I'm going to get 12 times 3 is a positive number, and in the parentheses, 3 minus 2 is a positive result. Positive times positive is positive. Our second derivative is positive, and that tells us again that that portion of the graph is concave up. Let's see here, I got the graph we can pull out, and let's see what this looks like. So here is our graph. We took the second derivative of this function, and we found a couple numbers. Those numbers were 0 and 2, and those were our points of inflection. So in our first interval from negative infinity to 0, we plugged in a test value and got a positive result. So here we are concave up. Our next interval went between the numbers 1 and 2. We plugged in the test value of 1, and we got a section that's concave down. And then we plugged in the value of 3, and we got another stretch of the graph here on the last interval that is again concave up. All right, and an important note here is the converse of this theorem is generally not true. That is, it's possible for a second derivative to equal 0 at a point, but that it is not a point of inflection. For instance, the graph of f of x is x to the fourth. You know, here it is in the figure. It's an upward opening parabola, but the fourth power makes it a little wider in the middle, as opposed to x squared. The second derivative is 0 when x is 0. If I take the second derivative, well, my first derivative is 4x to the third. My second derivative would be 12x squared. At the origin, at x is 0, this second derivative does have the value of 0. But this is not a point of inflection. We can see on both sides here we are concave up. So the second derivative is 0 when x is 0, but the point, the origin 0, 0, is not a point of inflection because the graph of f is concave up in both intervals. You know, here on the left, this is concave up. Here we are again concave up. Remember, points of inflection is where the graph changes from concave up to down or concave down to up. Okay, let's talk about the second derivative test. So in addition to testing for concavity, the second derivative can be used to perform a simple test for relative mins and max. This test is based on the fact that if the graph of a function f is concave up on an interval containing some point c, and the derivative, the first derivative of that point is equal to 0, fc must be a relative min. Similarly, if the graph of a function f is concave down on an open interval containing point c, and the derivative is equal to 0, f of c must be a relative max. So here in the box we have our theorem, the second derivative test. Let f be a function such that the first derivative is equal to 0 at this point c. And the second derivative of f exists on an interval that contains that point c. So we can plug that point into the second derivative. When we plug that first derivative critical number into the second derivative, if we get a positive output greater than 0, that tells us the point is a relative min. If the second derivative, we plug our first derivative critical number in there, we get a negative output. Then that tells us that the point is a relative max. If we have the case where the second derivative where we plug that point c in is equal to 0, the test has failed. And that means we may have a relative min or relative max or neither. In such cases, we have to fall back and try the first derivative test. And sometimes I think this is a little easier to see graphically. So I bring this up here. If the first derivative is equal to 0 at this point c, so point c we know is a critical number. We set our first derivative equal to 0 and we find point c. We take point c and plug it into the second derivative. If we have a case where that output is positive, we know that the graph is concave up, and that means our point c lies at the bottom of a valley, which means we're at a min. On the other hand, if we take our first derivative critical number and plug it into the second derivative and get a negative output, less than 0, we know that it is a relative max because the graph here is concave down. So let's try this out in an example. It says here, find the relative extrema of this function. And we're going to use the second derivative test to find them. So first, we want the critical numbers. We're going to find f prime of x and set it equal to 0. So 3 times negative, or negative 3 times 5 is negative 15, x to 1 power lower. 3 times 5 is 15, x to 1 power lower. And we want to set that equal to 0. Well, now on the left we can factor. And when I look at that, I like the 15. And we got a couple x's we can pull out. And I'm going to pull the negative out also. So I'm going to factor out a negative 15x squared. When I factor that out of here, all that is left is an x squared. And I factor it out here. I'm just going to factor the entire term out, but I change the sign from a plus to a minus because I did pull a negative out. And of course, this is a difference of squares, and that can factor down just a little farther to x plus 1, x minus 1. So we have 3 things multiplied equal to 0. That means we set each factor to 0. When we set our first term equal to 0, x is 0. Our second term is equal to 0 when x is minus 1. And our third term is equal to 0 at x equals positive 1. So these are the critical numbers we found with the first derivative, setting it equal to 0. We're going to plug these values into the second derivative to see if we're concave up or concave down. Or we're going to find the relative extrema, the mins and the maxes. So let's see here. First, let's plug the negative 1. And we got to find the second derivative. So we have f prime of x right here. I'm just going to derive that again. And before I forget them, let me write my numbers down over here. We had negative 1, we had 1 and 0. So f double prime, our second derivative. 4 times 15 is 60, and it's negative 60x to the third plus 30x to the first. So we take these first derivative critical numbers and plug them into the second derivative and check the sign out. So when I plug negative 1 in for this x and this x, I'm going to have negative 60 times negative 1 plus 30 times negative 1, or 60 minus 30, which is positive. And because that's positive, it tells us we have a minimum value. You know, this x value is the bottom of a valley because we know it's concave up above it. Now let's try the positive 1. When we plug a positive 1 into our second derivative, so we plug our positive 1 in here, and we'll get negative 60 times 1 plus 30 times 1, or negative 60 plus 30, which is negative. And when we get a negative output there, that tells us it is concave down, and if we're concave down, that point is at the top of a hill, or it's a max, a relative max. And we have one more x value to go, that is x is 0. When we plug 0 in, we get 0 plus 0 is 0, so we get f double prime is equal to 0, or the test has failed. Our test failed at that one critical number. But remember, we can always go back and perform the first derivative test that we learned about in the previous section. And if we do go back to that and use the first derivative test, we know here's our point 0. If we go back and do that, we will see that f is increasing to the left of it, and it is decreasing to the right, or it is increasing also to the right. So we know it's neither a min nor a max. So that's not a point of concavity at all. And that might be easier to see. Let me pull the graph up here. So here's our graph. We took our first derivative and set our first derivative equal to 0. So we found our critical numbers. We knew -1, +1, and 0 were critical numbers. So that meant there was a possible relative extrema above or below. So we could have done the first derivative test and found out the intervals where we were increasing or decreasing. Or with the second derivative test, we plugged this critical number into the second derivative and knew we were at a point where we were concave up. So we knew that that was the bottom of a valley, or a relative min. When we did x is +1, we plugged that into our second derivative, and we found out that it was concave down at that point, which meant we were at the top of a hill, or that point is a relative max. And the test failed at 0, and here's why. When we plug that in there, we can see that this is a point of inflection. It's not a relative min or a relative max. The test failed there. So we did go back to the first derivative test. When we looked to the left of that point, we saw the function was increasing. Our slope, or our tangent lines, had positive slopes. On the right-hand side of that 0, 0, our function was still increasing. So we went from increasing to increasing. So this wasn't a min or a max.